So this was a day 3 warm-up review for the midterm. I'm going to focus mostly on curve sketching. This is a nice little kind of synopsis of the relationships between f, f prime, and f double prime. Take a second, look over it. These are not 6 versions of the same thing or 6 copies of the same thing. The first one talks about being positive and negative. The second one talks about increasing and decreasing. And the third one talks about concave up and concave down. So if I were you, I would pause the video and just give this a 45-second once over. And then the two notes down there at the bottom, just to kind of help get it fresh and back on your mind for the relationships between all of these. Okay, so it's already been filled in, so we're just going to talk through this, so it should go faster. It says use differentials to approximate the value of cosine of 58 degrees. And one of the most important things is to remember that you cannot use the approximation formula with degrees. Everything has to be in radians. The formula for approximation is f of x plus f prime of x times delta x, which is the change in what you want versus what you know. So I have to, let's see, I have 58 degrees, so I'm going to let what I know be the 60 degrees. So off to the right, you can see I wrote x equals 60 degrees, which is the same thing as pi over 3. I know that I'm 2 degrees shy of that. So then you can see the negative 2 degrees. I'm going to times that by pi over 180 to turn that into radians, and that's going to give me negative pi over 90. And that is my delta x. That is what I want, which is the 58 degrees, minus what I know, which is the 60 degrees. And that's what gave me the negative 2. And then I turn that into radians. And so this is what goes there. Cosine of pi over 3 is 1/2, and negative sine of pi over 3 is a negative root 3 over 2. It said round your answer to 4 decimal places, so obviously this is a type it into the calculator. And something like this, the answer choices, if it was multiple choice, the answer choices would be extremely close together because they know that technically if you have a calculator, you can type in cosine of 58 degrees, making sure your calculator's in degree mode and get a decimal. So they want you to be accurate to 4 decimal places, and all of the answer choices are going to be extremely close. Straight up cosine of 58 degrees is not going to produce the 0.5302 exactly. So that's their way of making sure you're using the approximation formula. And also a reminder that there's no formula sheet for calculus, so you have to have that formula memorized. The function is twice differentiable, gives me f of 2, f prime of 2, and f double prime of 2. What's the value of the approximation of f of 1.9? Obviously, we're going to use 2. So I write my formula, and then I have f of 2 plus f prime of 2 times delta x. And they gave me all those values, so I'm just plugging them in. Delta x is going to be, again, what I want, which is 1.9 minus what I know. Want minus no. And that's why it's negative. And then just type that one in. Instantaneous rate of change is just another way to say derivative. So I need to find the derivative at -1. So I do a little low d high minus high d low over low low. And then when I'm evaluating, I don't stop and clean that up. I go ahead and plug in that -1. Um, be very careful with your algebra and your sines, but that's pretty straightforward. And feel free to pause and walk through the algebra yourself. That's totally fine to do that on your own. Determine whether Rolle's theorem can be applied to cosine of pi x on closed interval -1/2 to 1/2. If it can be applied, find all numbers such that f prime of c equals 0. Okay, so let's talk about the difference between Rolle's and MVT. And you can see off to the side, I've kind of written that out. Rolle's is a horizontal tangent line, and again, that finds peaks and valleys, because that's where horizontal tangent lines are going to be. The MVT says, I just want some tangent line that's parallel to the secant line that goes through 2 points. So MVT is where you go actually find the slope, like literally y minus y over x minus x, get that slope, and then set that equal to the derivative. But this is Rolle's, so I know that I want my slope to be 0. For both of these, you have to be continuous and differentiable, and that's where answer choice E comes into play. It would not apply if you are not continuous or differentiable. Cosine of pi x is a very well-behaved function, so that's all good. So let's see, I find f of -1/2 and f of 1/2, and those both turn out to be 0, so I know that f of a equals f of b. Now, they didn't both have to be 0. They could have both been, I don't know, an elephant. It doesn't matter as long as they are the same. That's what's going to make Rolle's apply, because the y values are going to be the same, which is going to make it a horizontal line. So again, they don't both have to equal 0. They just both have to equal the same thing. This has to be true. This is the part for Rolle's that is not the part for MVT. MVT, the y values are going to be different. For Rolle's, the y values need to be the same. That's what makes it horizontal. So again, these don't have to be 0. They just have to be the same. So then I take the derivative, which is a nice little turduck. I'm going to set it equal to 0 because the slope through any of a horizontal line is 0. And I divided by -pi. And then I said, okay, where is sine 0? And that happens at 0 pi and 2 pi. And then I'm going to divide by pi. And I get 0, 1, and 2. But my interval is from -1/2 to 1/2. And the 1 and the 2 are not in my interval. So I only want the 0. Number 5. Function is continuous on the closed. Gives me g of 1, g of 4, which is the following would guarantee that there's a number c. On the open interval 1 to 4, where g prime of c equals 1. All right, this is the MVT. I'm telling you that I want the derivative to equal 1. I want the slope of the tangent line to equal 1. So I am going to find the slope. So let's see, I have a 0.15, that's from here, and I have a 0.48, that's from there, and I find of the following which conditions would guarantee. I find the slope between those 2 points, and I get a slope of 1. But I really didn't need to do any of that, because this isn't asking me to find a value. This is saying which of the following would guarantee. So which of the following is needed for the MVT? Well, A says it has to be increasing. Well, it doesn't have to be increasing. G says it has to be differentiable. Yes, absolutely. It tells me that we're continuous. So I know I'm continuous, but it doesn't tell me that we're differentiable. And so that is something that I need. So again, that was one where I didn't need to write that stuff out off to the side. If I had read a little bit more closely, It's just talking about the conditions. It's not getting me to try to find an actual value. Number 6, the only function that does not satisfy the mean value theorem on the given interval is, so I have to be continuous and differentiable. A is a very well-behaved function. He's all good. B is not. He has issues at 0. However, that is not in his interval, so he is fine. C, a little tricky, but totally fine. Very continuous function, so he's good everywhere. D has issues at 0, and 0 is in that interval. So D is out. E is one of those that has a cusp, and I think the cusp is at 0, which is not in that interval. So D is the odd man out. Okay, so here we go. Now we're going to do number 7 where we actually get to find something. So the value of C that satisfies the mean value theorem for derivatives on the interval 0 to 5 for that function. Okay, so first of all, that's a very nice function. It's continuous and differentiable. So I need to find the slope from 0 to 5. So I plug in a 0, it's going to give me a 0, and I plug in a 5, and that gives me a 95. So now I have the 2 points, like the 2 endpoints, the one at 0 and the one at 5. So now I'm going to find the slope through those 2 points. So y minus y over x minus x, and that gives me a 19, which is a very steep slope. That's the slope that I want to be parallel to. So I want to find the place on the curve. So we're at 0, 0, and then at 5, 95. So, and then I don't know what the function looks like, but let's say he's cubic. So he does something like this. So what I'm doing is I'm trying to find the point where the tangent line is parallel to that slope. This guy right here, has a slope of 19. I want to find the tangent line that also has a slope of 19. So I'm going to take the derivative and I'm going to set it equal to 19. So again, it just really helps if you understand what you're doing and not just memorize the process. So I find the derivative, which is super easy. Set it equal to 19. And then it's quadratic. I can just add the 6, divide by 3, and square root both sides. Don't forget your plus or minus. But I'm in the interval 0 to 5, so I can't use the negative 1. And you do not have to rationalize your denominator unless it's multiple choice, and they do. Okay, number 8 is also an MVT. Applied to the function f of x, and that kind of looks like an f prime of x, but that's just f of x equals x squared, interval 3 to 9. Okay, and that's just the part that's written in there at the end, the f prime of c equals f of 9 minus f of 3. That's just the slope formula. They don't have to give that to you. And so it's kind of like, thanks for giving that to me, but it can, I don't know, be too much information and be confusing. So that's just the slope formula. Okay, so here we go. We've got f of x is x squared, and my two endpoints are, the x values are 3 and 9. So I'm going to get their y values to make some points. And so now I have 3, 9, and 981, and I'm going to go find the slope. I'm going to do y minus y over x minus x, and I get a 12. So then I'm going to take the derivative, and I'm going to set it equal to 12 because I want it to be parallel to that secant line who has a slope of 12. And I very easily get an x value of a 6. So the x value of a 6 is where the tangent line has a slope that is 12, which is parallel to the secant line that goes to the points 3, 9, and 981. Number 9, find two positive numbers such that the sum of the first and twice the second is 56, and whose product is a maximum. Okay, so this is optimization. Find two positive numbers such that the sum of the first and twice the second is 56, and that's that part right there. And the product is a maximum. There's my product. Now the product is what I'm trying to optimize. So that's what I want to take the derivative of, is the p. But right now it has two different variables, and so I want to get it in terms of one variable. So I'm going to take this one. And I think this is an old test problem or homework problem or something. And I remember noticing that on this one, a lot of you guys took the first equation that's highlighted and you solved it for y, which gave you fraction-y stuff, which doesn't make sense. It's so much easier to solve this guy for x and then plug him in for that x. It's just so much cleaner. I mean, not a big deal, but it's just cleaner. So then I'm going to distribute, and then now I'm going to pull the trigger and take the derivative of my product. I'm going to set it equal to 0 because that's what you do for optimization problems, and the reason is when I set the derivative equal to 0, it finds peaks and valleys, which are maxes and mins. So 56 minus 4y equals 0. Solve for y. I get y to be 14. Take that y value, plug it back into the first equation, so I can also solve for x. Find the length and width of a rectangle that has a perimeter of 48 meters and a maximum area. So perimeter is just an extra formula they gave me that I'm going to use to manipulate, but I want to take the derivative of the area because that's what I am trying to optimize. So perimeter of a rectangle is 2x plus 2y, and that's going to give me 48. I solved for y. This one would have been the same if you'd solved for x. Doesn't matter. They're both just as clean. So since I solved for y, then he goes in for y, doing a little distributing, and then this is where I take the derivative, and I set it equal to 0 because I'm trying to find the optimization. That gives me x equals 12, and then I take that 12 and plug it back in here to get my y value. I remember this one from the test review. At what value of h is the rate of increase of the square root of h twice the rate of increase of h? And this is just translating. You got the square root of h, and I want the rate of increase twice the rate of increase of h. Take the derivative, so it gives me 1/2 h to the negative 1/2. And then it's going to equal 2 because technically they're going to both have h primes, and so they kind of cancel each other out. Multiply both sides by 2, and then h to the negative 1/2 is 1 over the square root of h. Multiply both sides by the square root of h, and I divide by 4, and then I square both sides. Airplane is flying in still air with an airspeed of 255 miles per hour. If it's climbing at an angle of 21 degrees, find the rate at which it is gaining altitude. So the 21 degrees is a constant. Excuse me. X is the plane. So dxdt is 255 miles per hour. My theta is 21 degrees, and I want the change in the altitude. So I want dy dt. I'm going to use sine because I am dealing with opposite and hypotenuse. So sine of 21 degrees equals y over x, which is the same thing as y times x to the negative 1. Take the derivative of sine of 21 degrees and I get a 0. And then I do the product rule. So I'm here. Let's see. There's my leave it. Excuse me. Gracious. And then here's the derivative, and then there's the implicit, and then plus, and then this is the derivative of y, and then there's the leave it. And now I just need to plug in a whole bunch of stuff. I know that dx dt equals 255, and so that's m. I need an x and a y. So let's see. Oh yeah, this is where we said if we've been traveling for an hour and we're going 255 miles per hour, then x would be 255. So I plugged 255 in for, there he is, this x right here is that right there, and this x right here, nope, that's my dx dt. That's the dx dt. That is that x right there. So these two are x's. That's the dx dt. Didn't all fit on one line. I do need a y value. So I go back to this and plug in my x, which is 255. That's what I'm doing right here. Multiply both sides by 255, and I got 91.38. And that's where the y went in. And then all this is one big happy term, so I get a decimal with that. And then don't forget he's to the -1. So you have to do some fun algebra there and solve for dy dt. And again, I encourage you to pause it and run that through on your calculator. Number 13, find all critical numbers of the function. So critical numbers are where the maxes and the mins happen. So I'm going to take my function and take the derivative and set it equal to 0. Let's see, I'm going to GCF of 4x, and that leaves me with x squared minus 2, so I have 4x equals 0, and then x squared minus 2 equals 0, so I'm going to get a 0, and then a plus or minus root 2. So this should start to kind of remind you of candidates test and finding maxes and mins and that kind of stuff. It was the stuff right before optimization. So number 14 would be calculator active. So it says let f be the function with the first derivative, okay, of f prime being that very ugly formula. How many relative extrema does f have on the open interval, -4 to 2? I'm not going to walk through this on the calculator. I want you to pause the video and do this yourself. But I do want to talk about how do you know what you're looking for. So it says let f be the function with first derivative. How many relative extrema? So relative extrema is going to be where f prime equals 0. If you think about it, that makes sense. F prime equals 0. That's where the tangent line equals 0 is going to be at maxes and mins of f. Well, this is f prime, so I'm looking for f prime of x equals 0. So that would be where does it cross the x-axis, because its y value literally is 0. So now I want you to type this guy in. You need to make sure that you're in degrees. Type him in, and I want you to adjust your window so that you're only looking from -4 to 2, and you'll see that he's crossing 6 times. So go ahead and pause and type him in and make sure you're comfortable with that. Number 15, the derivative of the function is given by that thing on the interval, and I want to know where does it have a relative max. Okay, so again, kind of like number 14, but I don't just want to know where does it equal 0. If it's a max, the max is going to occur from when f of x is going from increasing to decreasing. So that's going to be f prime. If I'm increasing, then f prime is going to be positive, and then go to decreasing, and that's when f prime is going to be negative. So from above to below, so it's going to be doing this, not this. I don't want that. um, and on that interval. So again, pause the video, type that function in, adjust your window so that you're only looking from negative 2.5 to 2.5, and you're looking for where it crosses the x-axis, but it's going from above to below. Number 16, let f be the function with the derivative given by that. Okay, so that's a derivative with relative max. Okay, so this is the same as number 15, and this wants a max. So again, we're going from above to below. This is f prime. So I'm going to type this very ugly formula in, or function in, and adjust my window from -1 to 9. And I'm just looking for where it goes from above to below, where it crosses the x-axis going from above to below. So again, pause the video, type them in, adjust your window, and make sure you're very comfortable with that. Okay, number 17, 0 to 6, this is f prime. And again, just another reminder to be super careful and just aware of what kind of graph they're giving you or what kind of function they're giving you. Sometimes they'll give you f and ask for information. Sometimes they'll give you f prime and ask for information. So just make sure that you know what you're looking at. And this is the graph of the derivative. And I want to know a local max. So again, I want to know where f prime is going to equal 0. But if it's a max, it's got to be going, let's see, f is going to be going from increasing to decreasing. So f prime will be going from positive to negative. So we hit 0 here, but going from positive to negative happens at the 3. Okay, graph of the function f. Okay, so this is plane f is shown in the figure above, which the following could be the graph of f prime. So if this is the graph of f, I could do f is decreasing to, I don't know, I'm going to make some numbers up. I'm going to call him -1 and call him 1. So he's decreasing to -1, and then he's increasing to 1, and then he's decreasing. So I know that f prime would need to be negative, positive, negative. And the only one that happens at is at B. Take a second and make sure that you're okay. Remember, this is the graph of f prime, so negative, positive, negative. And he is the only one that does that. Okay, number 19, graph of f prime is shown. What intervals is f increasing? So f is going to be increasing where f prime is positive. That's highlighted in the graph. So we are positive from -1 to 3. Again, it's just knowing those relationships and what you're looking for. Number 20, let's see, that's f of x, and this is non-calculator. And I want to know, where is he increasing? So this is what I'm going to do, the sine graph. Okay, so if I want to know where he's increasing, and I don't have a calculator, so I can't graph him. So what I'm going to do is I'm going to base this off of the first derivative. So you can see off to the side, I found the first derivative, I set it equal to 0, and I solved and I got my critical values, so 0, 1, and 2. And I come over here to the left, and I put those on a number line. And then what I'm going to do is I'm going to plug these into f prime. And some of us keep getting confused as to where you plug these values in. So like I'm going to plug in a -1. This is going to be like a 1/2. And this is going to be like a 1.5. And this could be like a 3. So those are the numbers that I'm plugging in. But I plug them into, I go right there. And I'm not looking for the value, I'm looking for the sign of the value. So when I plug in a -1, he's going to be negative, he's going to be negative, and he's going to be negative, and that's where you see these three negatives. When I multiply all of them together, I get a negative. So I know that f prime is negative, so I know that f is decreasing. So this is the value of f prime. Again, that's why I'm plugging it into my derivative. And it gives me information about f. It doesn't mean that f is negative. It's f prime is negative, which means f is decreasing. And then increasing and decreasing and increasing. So I'm increasing from 0 to 1 and greater than 2. Okay, 21, calculator active. This says the first derivative of the function g is given by, okay, so that is the first derivative. It gives me an interval. On which of the following intervals is g decreasing? Okay, g is decreasing, and for some reason I've changed it to f. F is decreasing where f prime is negative. So f is decreasing where f prime is negative. And again, this is the graph of f prime or g prime, whatever. So I'm going to graph him. I'm going to very specifically adjust my window. Please make sure you're comfortable doing that by now. And I'm going to find where f prime is negative, which I did. And it looks to be on just on either side of 1. And the only multiple choice that handles that kind of an answer is C. All the other intervals are not, they don't split the 1. They're either one side or the other. All right, 22. The graph is concave down. Okay, so now we're talking second derivative test. Okay, so that's y. So the first thing I found is y prime, and then I went and found y double prime. And now I'm going to find my possible inflection points. So I'm going to GCF of 12, and then I factored it, and I got -6 and 2. I put those on a number line. I'm going to do my sine table, and I am going to plug like a -7 and a 0 and a 3. But remember, this is second derivative. Plug them into f double prime, so I'm going right here. And I'm getting a negative and negative. It's going to make him positive. Positive, negative, going to make him negative. Positive, positive, going to make him positive. And I want to know where we are concave down, and that is where the second derivative is negative. So that happens from -6 to 2. Number 23, the first derivative is given by that thing. And I want to know on what intervals is the graph concave up. So again, going to type him in, make sure you're in degrees, adjust my window, and I'm looking for where it f prime increases. All right, now this is asking about the concavity of f, which is really asking you to look at f double prime, but it's giving you the graph of f prime. So to find where f double prime is going to be positive, because that's going to make us concave up, then I need to know, remember, f double prime is the slope of f prime. So if I want f double prime to be positive, I need f prime to be increasing. Think about it like this. If I want f double prime to be positive, then f prime needs to be increasing. I also put in here that I used my table, so apparently I needed, these answers get a little close together, so not only did I adjust the window, but I also went over and used my table to find where it was increasing. Okay. 24. The derivative of the function is given by f prime of x. How many points of inflection? Okay. Points of inflection, that's where concavity changes. So, and this is the first derivative. So that's going to be where the first derivative has a slope of 0, not where the first derivative equals 0, but remember f double prime is the slope of f prime. And so if I want points of inflection, I want where f double prime equals 0, because that's where the concavity is going to change. So that's going to be at peaks and valleys or humps of f prime. So that's where I put where f prime peaks. And so I typed him in and I checked my interval. Um, and it happens, oh dang, I didn't even circle an answer. So I don't know what the answer is. Oh, it's 5. There it is. So type him in, adjust your window, and you're looking, and again, you're looking at the graph of f prime. So you're looking for how many times he peaks or valleys, and that it happens 5 times. Number 25, let f be the function with a second derivative. What are the x coordinates of the points of inflection? So they already give you the second derivative, which is really nice. So I know my possible points of inflection are 0, 3, and 6. Put them on the number line, and I do my sine check. Always be wary of a double root. Most of the time at a double root, the signs don't change. So a lot of times people will look at this and say, oh, it's going to have points of inflection at 0, 3, and 6 because they don't test the number line. But a lot of times, not all the time, but a lot of times at a double root, because that's from where that x squared equals 0, technically it's a 0 and a 0, the sign doesn't change. So the points of inflection are only where the concavity is going to change, which is where the second derivative test sign changes, which here only happens at 3 and 6. So very simple problem, but very easy to miss if you're not careful and think through it. Number 26, find all points of inflection on the graph. Okay, points of inflection are second derivative. So I take the first derivative and then I take the second derivative. And I got a 0 and a -2. I put them on the number line and did my second derivative test. Remember, you are plugging these values into f double prime, which just sits right there. And that's where these things are coming from. And my end result, and I want all points of inflection. So yes, it changes at -2, and yes, it changes at 0. And that's enough information to pick your answer, but they are points. So to get the y value that goes with -2, you go back to the original function because it wants the point on the original function. And the same thing with 0. You plug them both into the original function, and that's where the 0 and the -8 are coming from. 21, the graph of a twice differentiable function is shown in the figure below, which of the following is true? Oh, I love this problem. This is f prime, so this is just talking about the slope. So let's see, f prime of -1 is definitely a valley, so that's going to be 0. F prime of 0 is positive. That graph is headed upwards, so the slope of that graph is up. And then f prime of 1, that's definitely a negative slope. So that value is going to be negative. So then I just put them in order from biggest. Well, I guess you'd start with smallest. So the smallest would be the f prime of 1. And then you go to f prime of -1 because that would be your 0. And then f prime of 0, which would be positive. The graph of the function f is shown in the figure above, for which the following of the values is f prime of x positive and increasing. Okay, so f prime of x is positive, means that f of x, and this is the graph of f of x, and they're asking about information about f prime. So this is one of those ones where you can't just glaze over it. You got to really think about it. If I want f prime to be positive, that means that f of x is increasing. So no, and no, and no. So A, B, and D are out. And so I got that all based on f prime being positive. Now, f prime is increasing means that f double prime is positive. Okay, so let's make sure we understand that. F prime is increasing. Now remember, f double prime is the slope of f prime. So f prime is increasing, f double prime is positive, which means we are concave up. If f double prime is positive, we are concave up. And C is not concave up. So, got to be E. All right, 29. Figure above shows the graph of f prime. The derivative following best describes the graph of f. Okay, so again, this is f prime. So I came over here and just did this number line. So f prime is positive. Looks like to -2. And then it's negative to 1, 2, 3, 4, 5, 6, 7. And then it becomes positive again. So that means that f is increasing and then decreasing and then increasing. So if I'm increasing and then decreasing, there's going to be a max there and there's going to be a min there. So it says, so C, D, and E are out. C says 2 relative extrema, 2 relative mins, 1 max, no. 2 and 1, no. 2 and 2, no. 1 and 1, yes. 1 and 1, yes. Okay, so 1 max, 1 min. So now we got to go based on points of inflection. So now we need to start thinking about second derivative. And again, this is the graph of f prime. So f prime is increasing, then f double prime is positive. Again, f double prime is the slope of f prime. So if f is increasing, again, not talking about positive or negative, we did that up here, but if f prime is increasing, f double prime is positive. So increasing here and here. So let's see, it looks like -1 to 2, 1, 2, 3, 4, 5, 6, I don't know, to maybe 6. So, and those numbers aren't really important. It's how many times it changes. So it goes from decreasing to increasing to decreasing to increasing. So 1, 2, 3 times it changes. So 3 points of inflection. And that's why it's A and not B. This is a really great problem because it really makes sure that you understand the connection. You had to go from f prime to f, so kind of backwards, but then you also had to go from f prime to f double prime, and that's more of a forward direction. So just making sure that you understand those relationships is super important. Okay, number 30. Twice differentiable function, open interval a to b, f prime is positive. That means that f is increasing. So can't be D or E. F double prime is negative, which means we're concave down. So it has to be C. Okay, 31's calculator. They give me the first derivative. They give me a very specific interval, so you're going to pause and get all that typed in and fix your window and all that wonderful stuff, and then you're going to say, okay, I'm looking at the graph of f prime. The questions are all asking you about f. So I'm going to graph him, and I can see after I graph him, and I hope you've already paused it and graphed it. Again, this is f prime. Looks like he's positive and then negative, and it changes somewhere in between 1 and 2, kind of closer to the 2. So if f, so it says f has a relative max. So positive, negative, yeah, it would have a max. Yeah, has a max right there, somewhere in between, somewhere on the interval from a 0.4 to a 2.4. Yeah, absolutely. F has a relative min? No, because it doesn't go from negative to positive. It goes from positive to negative. So 2 is out. So 2 is out. And 1 is true. So now I just have to see if 3 is true. The graph has 2 points of inflection on the interval. Okay, inflection is second derivative. Second derivative is the derivative of f prime. So if f prime is increasing, f double prime is positive. If f prime is increasing, f double prime is negative. And that's just me just kind of writing out to get all my facts straight. So inflection points are at all peaks of f prime, where it changes from increasing to decreasing. And this graph has 2 peaks, if you look at the graph. So that is true. It does have 2 points of inflection. So again, you need to make sure that you're pausing the video and graphing this and checking the intervals. 32, I love these problems. This is non-calculator. It gives me f prime and f double prime, and it says which ones are, over what intervals are we both increasing and concave up. So I take my critical values for my f prime, which is going to be 0 and 1, and I do the first derivative test where I plug those values, or not those values, but values in those intervals into f prime, and do my sine chart and find out where he is increasing, which appears to be greater than 1. And then I take my second derivative, which looks like my points of inflection are going to be 0 and 2/3. So you can see where those are on the number line. And then I do my sine test for second derivative for concavity. So I can see that he's concave up. He's concave up when he's less than 0, when he's greater than 2/3. So he's concave up and increasing, looks like from 1 and up. So yeah, Roman numeral 4. Okay, number 33. Oh yeah, these are good. Function of f is continuous on the closed interval 2 to 4 and twice differentiable on the open interval 2 to 4. Gives me f prime of 3. This tells me that f double prime is negative, so I know I'm concave down, which the following could be table values for f. If I know that f prime of 3 is 2, then I know the slope at 3 is 2, and f double prime is less than 0. I know that I'm concave down. So that's me just drawing conclusions based on what they said. So I need to have a slope at 3 of 2, and I need to be concave down. Just to, like, let's look at D. D has a slope. This is increasing by 1 each time. This is increasing by 2 each time. So he is linear, and that's not going to be concave down. This one, I can look at this one and say, okay, he's increasing by 1.5 and then increasing by 2.5, and so that's going to be concave up because he's increasing a little bit and then a little bit more. So that's going to make him concave up. B does not have a slope of 2, so if I'm looking for the slope at 3, I'm going to find the slope between the 2 points on either side of it. The 4.5 is me subtracting my y's, and then the 2 on the bottom is me subtracting my x's, and that does not give me a slope of 2, and c is the same thing. That gives me 3.5, and that gives me a 2, and that slope is not a 2, so he's out. This one, if I did y minus y, that would be a 4 over x minus x would be a 2. So his slope is a 2, so that's good. And concave down, so this is going up by 2.5, but then it's only going up by 1.5. So think about it. If you go up 2.5, but then you only go up 1.5, that's going to make you concave down. And that's why he works. Okay, last two problems. Hang in. Table above gives values of the function f at selected values. Be very careful. These are not all the values. If f is twice differentiable on the interval from 1 to 5, which the following statements could be true. If I look at my y values, I can see that it's going down, going down, going down. It looks like it's going down by a little bit and then, or by a lot, and then it's kind of letting off the gas a little bit. And this is for f. So the slope is definitely negative, so f prime is going to be negative because f prime represents the slope. So I know anything that says f prime is positive is out. But I can also see that the slope is increasing because it's getting less negative. So if the slope is increasing, then f prime, which represents the slope, is also increasing. And that's why it's B. Let f be the polynomial function with values f prime selected, which the following must be true for -2 to 6. So again, I made a chart of just looking at the y values, and I can see that from 3 to 1, the derivative is decreasing. So f double prime is going to be negative. So I know we're concave down. And then from 1 to 7, it's increasing. I can't say it. F prime is increasing, so F double prime would be positive. So F is concave up. And then again, we are decreasing, so it's going to be it. So F double prime is going to be negative, so F is going to be concave down. So I know that there are at least 2 points of inflection. Could be more than that. Because these are not all the values, but I know that it has at least 2 points of inflection, and that's why it's B. All right, this one was packed full of information, so I hope that you take your time and don't feel like you have to go through this as fast as I did, and I hope you press pause and messed around with your calculator and did some thinking on your own and some processing before you moved from problem to problem. And then you've got a set of problems to work on to help you practice this section to get you ready for the midterm.